Good morning, guys. Today I want to talk about inverse functions. Now, we talked about a lot of inverses throughout the course. We did inverse matrices. We talked about within our transformations how horizontal transformations are always the inverse of what shows up within the equation. So we use this word inverse a lot. And inverse needs to mean to us that it's not the opposite, but the undo operation. So that's what we need to think when we see the word inverse. We need to think undo. So the inverse of adding something is subtracting it. The inverse of multiplying something is dividing it or multiplying by reciprocal. And that's why we use the word additive inverse when we're talking about the opposite of something, because it cancels it out. It gives us zero, the identity, the additive identity. Or multiplicative inverse when we're talking about multiplying a number by its reciprocal or dividing it by itself, because they give us the multiplicative identity, which is 1. We talk about an inverse matrix. The product of inverse matrices is equal to the identity matrix. So we use this word inverse a lot, and we just need to get the idea that it means it undoes whatever that particular operation was. So we can really generalize that when we're talking about functions, and that inverse functions, we were talking about the composition leading to just the function x. So inverse functions completely eliminate each other to the extent that all we're left with is just a list of the domain values. So that's what inverse functions say. F of g of x should equal x, and g of f of x should equal x. If that occurs, then g is the inverse of f, and consequently f is the inverse of g, so they are inverses of each other. So the composition of the function gives us x, which is our identity function. Now, notation-wise, we'll use this -1 exponent. We would say f inverse of x for this, and that doesn't mean reciprocal. It's just that, just like we did with the matrices, a -1 on a matrix was not reciprocal. It just denoted inverse to us. So that's just saying the inverse of the function of f. Now, what's going on? The reason that they cancel each other out, that they undo each other, is because the domain of one function is going to be the range of its inverse. And the range of the function is going to have the same domain, or is going to be equal to the domain of the inverse. Now, what that's doing is, if I take a function, if I take a value rather, and plug it into a function, so the input of this function then becomes the output, input of this input value becomes this, has this output value, and then when we plug that back into here, the reason it takes us back is because all the outputs for this function are the actual inputs for this function. So the range values for one become the domain value, or are the domain values for the other. And so we just go in this never-ending circle of moving into the domain. Well, that puts me right back over here. And then moving back into here, and that puts me right back over there, because they're inverses of each other. Now let's kind of get out all this conceptual stuff and get into some actual numbers. Say we have these two functions here. F of x is equal to x square root of x plus 1. And g of x is x squared minus 1. And we're going to limit the domain on this particular quadratic function to just the x is greater than or equal to 0. So conceptually, if we talk informally, inverses should undo each other. So what are we doing to our x's here? We're adding 1, and then we're taking the square root. Well, what's going to be the inverse of all that stuff? Well, the inverse of taking a square root is squaring it, and the inverse of adding 1 is subtracting 1. So we can see informally what's going on right here. Well, if we looked at it just like we did here in terms of composition, if I take my f of g of x, f is going to be my output function, and then the g function is going to get plugged into it, and the domain just comes into how we define stuff. It doesn't come into the actual calculation parts. Well, we can see -1 plus 1 is going to cancel, so we're left with x squared, which is, or square root of x squared, which is equal to x. So f of g of x equal to x. They completely canceled all the extraneous operations out. Now, let's do g of f of x. G of f of x, now we have g is the output function, so something squared minus 1. F is the input function, square root of x plus 1. And again, square is square root. and you're going to be left with the radicand. X plus 1 minus 1 cancels, so we're left with just x. So since f of g of x and g of f of x both equal the identity function x, we can say that f and g are inverses of each other. So that's algebraically how we can just use this definition of composition. But let's look at it numerically. Let's say we have a table. Let's say that we have x is equal to -1, 0, 3, and 8. So in our f function, f of x is equal to, well, -1 plus 1 is 0, square root of 0 is 0. 0. 0 plus 1 is 1, square root of 1 is 1. Try 3. 3 plus 1 is 4, square root of 4 is 2. And then 8 plus 1 is 9, square root of which is 3. Let's kind of flip this around and say that if we had our g equation, let's use these values right here, 0, 1, 2, and 3, and see what happens. So 0 squared is 0, minus 1 is -1, and then 1. 1 squared is 1, minus 1 is 0. And 2. 2 squared is 4, minus 1 is 3. And then 3. 3 squared is 9, minus 1 is 8. So what do we notice happens from one function to its inverse? The domain values for this function are -1, 0, 3, 8. Well, that's what the range values, the output values for the inverse function happen to be. And the domain values for this function were the range values for that function. So it just fits back into the domain of one is equal to the range of the other. So that's how we're actually creating these inverses. We're just swapping the domain and range of each of those functions. Well, graphically, if we were to do that, just swap the domain and range. If I took my f function, I'm going to give myself some room to write right here. So if I plotted just all these points, x is -1, 0, 0 is +1, 3 is +2, 4, 5, 6, 7, 8 is +3. So we get this function right there. Well, if I was to look at my g equation, so this was f of x. If I was to look at this g equation, the graph for the g function, 0 is at -1. So over 0, down 1. 1 is at 0. 2 is at 3. And 3 is all the way up here at 8. Somewhere up in here. So we get, we'll pretend that went through those points. But we get this function right here, the g of x function. Well, what's very, very interesting about this is, if I was to see how we are symmetric across this line right here, how we've taken this f function and flipped it across this line right here, where to get this g function. What do you think the equation of that line is? And it's the same line for every single set of inverse functions. All inverse functions are symmetric about this one line, or across this one line. Well, look at what that line is. That's the line y equals x, right? 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and so on. So this is the line y equals x. So we notice that all inverse functions are symmetric across the line y equals x, because that's where your domain and your range are equivalent across on that line. Because the y values and x values are equal, so all domain values here are going to be equidistant from that, so all range values for this function will be equidistant from that line. So that's why they're all symmetric across that line, every single function. So we've got a lot of different ways to look at functions. We can look at them graphically and say that, They're symmetric across this line. We can look at them numerically. The domain of one became the range of the other, and the range of one became the domain of the other, and so on. We can look at them as compositions. We can look at them informally, just kind of talking through it. Did we cancel out every operation to get the other? But when we go to actually calculate inverses, we want to figure out what the inverse of a function is. Say I have f of x is equal to 5 over x minus 2. It really goes back to this idea right here of the domain of one becoming the range of the other. Well, inside of a function, what do we use to represent the domain and the range of the function? Well, we represent the domain with the x, and we represent the range, the output, with the f of x. Well, just to make it a little cleaner, I'm going to represent it with a y. So if we are swapping the domain and range, all the domain values of one function become the range values of the other function, then my representative of that domain needs to swap also. So we are literally going to swap the domain and the range within the function. Take x and make it equal to 5 over y minus 2. And in this particular example, that we're going to find the inverse. Find f inverse. So when I'm doing that, just swap x and y and then go through and isolate your variable. So right now we have a rational equation. We put it over 1, cross multiply. We get x times y minus 2 equals 5. And then go through and isolate y. So divide by x. So we get y minus 2 equals 5 over x. And then we add the 2 on over. So we get y equals 5 over x plus 2. So that should be f inverse of x. 5 over x plus 2. So that's the inverse of 5 divided by the quantity x minus 2. So that's how algebraically how we calculate inverses, or how we find inverses, is by literally taking the x and y, swapping their places, because we're simulating swapping the domain and range of our function. And then we just go through and resolve. We redefine it for the new x. So we solve and isolate the y, and that gives us our inverse. We would go through and check, compose this function by this function, and this function by that function, and you see that they both will equal, both compositions will equal x. They are inverses of each other. Now, when we talk about inverses, sometimes we say inverses, sometimes we say inverse functions. And that's a very important distinction. Everything I can swap the x's and y's on. It takes no effort, no thought to just take this list of x's, this list of y's, and then swap them. That's creating an inverse. But is that inverse going to be a function? And that's where we need to look at one-to-one functions. So give me a second, I'll get that information about one-to-one functions up here, and then we'll talk about those. So one-to-one functions. One-to-one functions say that we know the rule for a function. For every element of the x, there's exactly one y value associated with it. Well, one-to-one function takes it a step further and says that if a function is one-to-one, not only is it a function, because it's a function, but not just the x's have one y associated with them, but the y's have only one x associated with them. So that's why it's one-to-one. Every x and every y only have one value that go to each of them. So it's unique, they each have a unique value associated to them. They're associated to each other just one time. Well, what's that mean kind of graphically and in terms of inverses? Well, for f inverse to be a function, then f of x must be one-to-one. F of x can have an inverse, but that inverse cannot be a function unless it matches this. And just think about what's going on there. What does inverse mean? It means the domain and the range swapped. So if the domain of the original function has only one y value with it, and the range has only one x value with it, when they swap places, now the new domain has only one range value with it. So that's why we need to be one-to-one for the inverse to actually be a function, and not just some inverse relation. So let's look at some examples here of functions. And we can see it when we look at it graphically too. So if I took x cubed minus 1, well, x cubed minus 1, when we graph that, we're going to get shifted down 1, and then we have our 1 by 1 box. Remember all of our transformation work we've talked about before. So that's x cubed minus 1. Well, the inverse of that would be the cube root of x plus 1. Add your 1, take your cube root, all that good stuff. Well, the graph of that we can get just by doing our reflection, right, across that line right there. So when we reflect it, we're going to get there, because instead of it being over 1 down, or over 1 up 0, we're going to go up 1 over 0. Instead of it being over 0 down 1, it's going to be back 1 up 0. And then this one here where it was left 1 down 2, left 1 down 2, we're going to go down 1 and right 2. Which should put us somewhere over here. And as you can see, my line is not very accurate because I don't space things correctly. So should have given us something along those lines there. Okay, so we should get that function and up 1 over 2. That's where we're at. That function. Oh, I was right the first time. Hard to graph these when you don't write out the coordinates for all the points. So we can see how it reflected and gave us this new picture. Well, think about how we check the graph of a function to see if it is a function. We use the vertical line test, correct? Well, on my original function, if I do the vertical line test on it, it passes. It's a function. X cubed minus 1 is a function. Good job. Well, when I take that graph and I reflect it across this line, my vertical line test for my function has become what line test for the inverse function? It's become a horizontal line test. So that's what's going on when we're talking about this one-to-one. To test for one-to-oneness, we're actually going to run a horizontal line test. Horizontal line test tells me nothing about the actual function. Horizontal line test tells us if f inverse of x is a function. If f inverse of x is a function. So let's take the x squared minus 1. X squared minus 1, shift it down 1, right and left, 1. And we get this function right here. That's f of x. That's x squared minus 1. Is this inverse? Is the inverse of this function a function? Is this a one-to-one function? Well, we can see easily that's not, because when we run the horizontal line test, there are infinitely many horizontal lines. And it only has to fail with one line. But there are infinitely many lines that have more than one y coordinate for it, or more than one x coordinate for each y coordinate. So that's why it's failing this one-to-oneness, because every element of the range does not have just one domain value. There are infinitely many elements of the range that have multiple domain values, multiple x values with them. So while x cubed minus 1 is a function, x squared minus 1 is not a function. Now, that kind of gets into where our first example that we looked at, we had that little stipulation on the side where x is greater than or equal to 0 on our f of x. Let's look at why that's there and why we need that there, why it's so important that we have that. So, if I look at how I actually calculated this function, we said f of x was equal to square root of x plus 1. And I want to find the inverse function of that. Well, first off, is the inverse a function? Let's look at the graph of that one more time. So if I look at f of x equals x plus 1, is it a one-to-one function? So There's -1, +1, connect my line. All right, so this is f of x. Is this a one-to-one function? Does this pass the horizontal line test? Well, I can run infinitely many horizontal lines, and we say yes, it does. This passes the horizontal line test, so the inverse of this should be a function. Well, here's the issue with that. Solve this. Find its inverse. Well, when I take y equals square root of x plus 1 and I swap them, I get x equals square root of y plus 1. Then we go through, it's a radical equation, square both sides. X squared equals y plus 1, move the 1. So y equals x squared plus 1. So we can say f inverse of x is equal to x squared plus 1. Oh, there's a little something wrong with that. Because remember, if they're inverses of each other. They're inverses of each other. Well, if I graphed that, x squared plus 1, I would shift, x squared minus 1, called it. I would shift right down 1, and I would get this function right here. Let's do it in blue. This function right here, well, that's not a mirror reflection across my y equals x line. This portion of it is. The part to the right of the y-axis, but the part to the left axis is all this extra stuff. Let's go where domain and range come in. F of x was a one-to-one function. The inverse of f of x has to be a function. Let's write out what the domain of this function is. Domain of this function is where the radicand is greater than or equal to 0, so x is greater than or equal to, x plus 1 is greater than or equal to 0, so x is greater than or equal to -1. And we can see that graphically. X is greater than or equal to -1. The range, if we looked at my graph, is from 0 up, right? 0 is our global minimum, and then the graph just keeps increasing. So the range is x greater than or equal to 0, or from 0 to positive infinity. And well, we said if this is the inverse of this, by rule, the domain of one must become the range of the other. So the domain of f inverse has got to be the range of f. Well, what was the range of f? Y greater than or equal to 0. So the domain of f inverse has now got to be the range of f, so that's going to be x greater than or equal to 0. The range of f inverse has got to match the domain of f, so that's got to now be y greater than or equal to -1. So if we adjust our graph to meet the rules of domain and range swapping for inverses, if the domain can only be greater than or equal to 0, that means the left side of this f inverse curve does not exist. So now our function has met its one-to-oneness in that it passed the horizontal line test and its inverse passed that vertical line test. So we can see why we had to have that little domain restriction on there is because f of x had a restricted range. It wasn't positive infinity, negative infinity. There's a lot of stuff going on there, and that means we have a restriction on the domain of its inverse. So a lot of very interesting things there about inverse functions. Domain and range swap. To calculate them algebraically, we just actually take the x and the y variables, swap their places, and just solve for your y in its new location. That'll give its inverse. And to determine if the inverse is a function, we run that horizontal line test to test for one-to-oneness. That's it for inverse functions, and I will see you in class tomorrow, guys.